Welcome to the third of our three-part installment on amplifiers. In this lesson, we'll take a look at several example amplifier circuits. Let's begin by looking at what's called a difference amplifier. Recall our two rules from the last lesson, I plus and I minus, the currents going into our non-inverting and our inverting inputs, they're both equal to 0, or in other words, the input impedance of my op-amp is infinite. And the second is this notion of negative feedback, which I do have here in my circuit. You'll notice in my feedback, I have a resistor R2 in the feedback path. And this is going to imply that both of my inputs are equal. So V plus is equal to V minus in this case. And so the general approach to solving these op-amp problems, or looking at the performance of op-amps, will be to evaluate the voltage at the non-inverting side, the non-inverting input for my op-amp. We'll then apply that voltage to the inverting input of our op-amp, and then use some basic Ohm's law or KCL equations to determine what the output is in terms of the input to the op-amp. So let's begin. We're going to start this process by trying to determine what the voltage is at this non-inverting input of my op-amp. So we need to figure out what is V plus. So V plus in this case, you'll notice I have a voltage divider here, right? I have an input VI2, there's another input to the op-amp VI1, we'll come back to that in a second. But looking at VI2, I have two resistors and ground. So I have a voltage divider here, and I can use that to describe V plus. So V plus will be equal to R2 over quantity R1 plus R2 times that input VI2. And then since we have negative feedback in our op-amp here, we can say that V plus is equal to V minus. So we'll go ahead and say that V minus is now equal to R2 over R1 plus R2 times VI2. KCL then tells me, Kirchhoff tells me, that the current through this path is going to be equal to the current through this path because we've defined here that the input current is 0. I minus is 0. So this current will be equal to this current. And as a result, I can write that as VI1 minus the voltage input to my non-inverting input of my op-amp. So here's V plus, all divided by R1. That's going to be equal to V plus minus V out, all divided by R2. If I substitute in this expression for V plus, I'll end up with the following description of V out. So here V out will be equal to R2 over R1 times the quantity VI2 minus VI1. And so what I end up with is the difference of my two inputs, hence the term difference amplifier. I have the difference of my two inputs, VI2 minus VI1, times some gain here, R2 over R1. Now, I want to be very clear that this gain, R2 over R1, this is separate and distinct from the internal open loop gain, AV, the gain of the op-amp itself. So this gain, this R2 over R1, this is the gain for the entire circuit, looking from my two inputs, VI1, VI2, to my output, VO. Now, of course, this isn't a perfect circuit. If I were to put a sensor, connect that sensor to VI2, the input impedance that that sensor would see is going to be the sum of these two resistances, so R1 plus R2. And so if I chose those as a couple kilo ohms, that wouldn't be a very high input impedance. Well, let's consider then if we were to connect the inputs of our op-amp circuit to a voltage divider. So there'll be two resistors, I'll call them both R0, as well as another voltage divider, R0, and then I have some variable resistance here. So maybe it's a potentiometer, or maybe in terms of a sensor, it's a temperature sensor. But because I have this potentially small input impedance, I can have some potentially significant loading on this circuit, depending on what this nominal resistance is, depending on the value of R0. So let's suggest a better option then. So instead of using a single op-amp circuit like I've drawn here, I can actually use multiple op-amps to perform this task. So in this circuit, I still have my difference amplifier, but now in an attempt to overcome the small input impedance associated with this difference amplifier, I also now have some unity gain buffers that are acting as an isolation layer. So this entire circuit, this is what's known as an instrumentation amplifier. So now we have the ability to do our difference amplification But we also have now this high impedance op-amp circuits, or two of them in fact, with these unity gain buffers, such that now we're properly connected, right? The sensor is seeing an input of a very high impedance, and then the output to my differential, to my difference amplifier rather, is a low impedance. Let's take a look now at another use for an op-amp circuit, and this time we'll take a look at a DC offset. Consider some signal coming off of a sensor, and let's say that's in units of volts with respect to time, and the signal has some offset. And most often I actually don't care about the DC offset. That's usually an artifact of how the sensor or the system is set up, but I am typically very interested in the AC component of that signal. And so the problem that I have is that if I connect this signal up to a standard inverting op-amp, often I'll have a saturation occurring, right? Because the maximum output I can achieve is going to be driven by these rail voltages associated with the power supply that I've connected my op-amp to. So if I have a significantly large DC offset associated with my signal, I'll actually get some saturation occurring. I'll actually get some clipping of these larger amplitude AC components. And so what I really want to do is I really want to remove that DC offset. I really want to get this DC offset, this average signal line, down around 0 volts. And a great way to rid ourselves or to get rid of this DC offset is to take a look at this virtual ground. So instead of putting ground here connected to the non-inverting input of my op-amp, I could put any voltage there, right? So I could accomplish that with something like a voltage divider. And so in this voltage divider, we could select R3 and R4 such that this reference voltage input to the non-inverting input of my op-amp, such that that reference voltage is now equal to that DC offset that we were trying to remove. So let's explore this a bit. I have a negative feedback configuration for my op-amp with an impedance in the feedback path. So if I have a VREF at my non-inverting input, I now have a VREF at my inverting input. And so if I look at Kirchhoff, I'll find that VI minus VREF over R1 will be equal to VREF minus Vout over R2. If I multiply my R1 and R2 by both sides and then simplify a bit, I'll find that my output voltage is described now in terms of a minus R2 over R1, so the ratio of this feedback resistor over this input resistor R1, times the quantity VI minus VREF, all of that plus VREF. So it's this V1 minus VREF term that's removing the DC offset. So if I had something like a DC offset of maybe 3 volts, right, this would effectively shift the entire voltage down, and then that AC component would now see the overall gain associated with R2 divided by R1, and since we're connected to the inverting input, everything will be inverted in terms of sign. Now, in the end, that reference, that DC offset, is ultimately added back into my output, but it's the, in this example, it's the AC component of interest that's getting amplified. So now let's look at another circuit where instead of just resistances in our circuit, we now incorporate a capacitor. We'll begin by looking at the impedance associated with the capacitor. So the impedance of the capacitor is 1 over j omega c. So at high frequencies, this is acting as a short, and at DC, it's blocking. The voltage at my non-inverting input, that's ground. And since I have this impedance in my feedback path, that means that the voltage of my inverting input is ground as well. And once again, we can apply Kirchhoff by looking at these two currents. This current going into the inverting input is going to be equal to 0. Both currents are going to be equal to 0. I plus and I minus will both be equal to 0. And so VI minus ground, or 0, divided by R, the resistance of my resistor, is going to be equal to 0 minus Vout over ZC, the impedance of my capacitor. And this gives me a voltage output equal to minus ZC over R, all times VI, my input voltage. And so if I substitute in for ZC, I'll find my output voltage is now equal to minus, since it's an inverting op-amp, minus 1 over j omega times RC, all times VI, the input voltage. Now, it's important to appreciate that the way this is set up, we're currently looking at the output in the frequency domain. Now, we could look at that in the time domain as well, where V out with respect to time is equal to minus 1 over RC. And because of this 1 over J term, that's effectively an integral, I now have minus 1 over RC times the integral of my input voltage with respect to time. And so this is often referred to as an integrator circuit. If you are working with PID controllers, for example, if you're doing some control theory, this is a very common approach to building the integral component of the proportional plus integral plus derivative controller, the PID controller. Another application where these op-amp circuits are often used is with piezoelectric sensors. So piezoelectric sensors, they operate with a material that will generate a charge proportional to the displacement. So if there's a stress or a strain in the material, the charge will be proportional to that stress or strain, or equivalently to the displacement. So a typical application, typical use of these sensors would be something like an accelerometer or a force sensor. So we could write this as a VI, an input voltage, will be dependent or equal to R times dQ dt, where Q is the charge. So we're looking at the change in charge with respect to a change in time. So I could rewrite this expression of my output voltage with respect to time for a piezoelectric sensor as the V out will be equal to minus 1 over RC times R times the integral of dQ dt dt. And you'll notice the R's cancel, so I can rewrite this as minus 1 over C times Q of T. And so this op-amp circuit, it's often used as an integrator, and in this case, it's also useful as a charge amplifier.